Okay, this is Mr. Ferguson. I'm flying solo today, and we're doing the second part of video 3A.4, where we're going to teach you about average atomic masses. So, average atomic mass is actually what's reported on the periodic table. So when we look at a periodic table entry for an element, like let's take carbon, the atomic number is going to show up at the top, that would be 6 for carbon. And then that number that's at the bottom, like the 12.011, that is the average atomic mass. So as we've already learned, there are different isotopes of pretty much every element. And the isotopes are atoms that weigh a different amount than other atoms of the same element. Now how can that be? Well, if you remember, they all have the same number of protons if they're the same element, but they don't necessarily have to have the same number of neutrons. So some atoms can have another neutron or two than others, and we call those different numbers of neutrons or different mass atoms, different isotopes. So what's actually published on the periodic table is an average for all of the naturally occurring isotopes, the ones that are out there in the atoms in nature. But it's not just a simple average like you might do if you were averaging together, two test grades. It's what's called a weighted average. So let me illustrate the weighted average concept with my basketball team illustration here. So let's say on our basketball team we have 5 players, and 4 of the 5 players are very tall, 2 meters, and the 5th player is much shorter, only 1.5 meters. So let's say we wanted to know the average height of the players on our basketball team. Well, with a small number of numbers like this, you could simply add those up, and you of course get 9.5 as the total height, 9.5 meters, and we would divide by the number of numbers, 5, and we're going to get an average value of 1.9 meters. So you can see from our average that it's reflecting the fact that there's not equal numbers of tall and short players. There's definitely a predominance of tall players, and the average is closer to the value of the height of the tall players. 1.9 is pretty close to 2. It's not all that close to 1.5. This is a weighted average just by virtue of the fact that there's more. So how do we do an average atomic mass? I mean, atoms are small, and even looking at a tiny sample of them, there's going to be billions and billions and billions of atoms. You can't add them up as numbers. What we can do is take published values for like the abundances of the atoms, and we can work with it that way. Let me see if I can illustrate this with the basketball concept, though, before we move into a real problem. So let me shift this off to the side here, and let's rethink that basketball problem. One way we could look at it is we have 80% of the players on the team have a height of 2 meters, and 20% of the players on the team have a height of 1.5 meters. So if we turn those percentages into decimals, and we basically just multiply each percentage times the value it goes with, that's going to give us 0.8 multiplied by 2 meters, and 0.2, which is 20% turned into a decimal, multiplied by 1.5 meters. And if we work out that 0.8 times 2 is 1.6, 0.2 times 1.5 is 0.3. And if we just sum those up, 1.6 plus 0.3, we get 1.9 meters, which is exactly the same value we got by doing the traditional average method, where we just add them up and divide by the number of numbers. And you'll see why this approach works for atomic isotope averages when we get onto the example problem, which I actually have right here at the bottom of the page, so we'll just slide that out of the way here, and we'll bring this up. So let's take nitrogen. There's actually only two naturally occurring isotopes of nitrogen. There's nitrogen 14, which has 14 particles in its nucleus. 7 are protons, 7 are neutrons. And there's nitrogen 15, which again has 7 protons in its nucleus and 8 neutrons. And you can see the abundances. Nitrogen 14 predominates. It's over 99%. So if we wanted to find the average atomic mass, we would simply take 14 multiplied by 99.63 turned into a percent, which will be 0.9963. I'm just going to put that in parentheses, and I'm going to add to it the second mass of the second isotope, 15, multiplied by its percent abundance. Now here's a little tricky one because it's less than 1%. It's 0.37, so we still need to shift that decimal 2 places to make it a decimal. So that's going to be 0.0037. And you can do this with any number of things. As you see, the next example is going to have quite a few more. The main point I want to emphasize is this is fairly simple math, but if you don't want to do it in steps and you want to do it as one calculation string, like just entering that into the calculator, be sure you use the parentheses. So I punched this into my calculator, and what my calculator is telling me the average atomic mass for nitrogen would be 14.0037, which is not all that far off the published value on my periodic table. Actually, my periodic table says 14.01, and then the other version says 14.0067. But they're all going to vary depending on whose data they used. So, if you calculate and it doesn't necessarily match up to what's published on the periodic table, that's actually not unusual. The different periodic tables won't even agree with each other. But we are going to ask you on a test to take the relative abundances, which would mean, when we give the percentage of each isotope, and figure out what the average atomic mass would be for that relative abundance. So let's do one that's the same math but just a little more involved. Alright, so here are the naturally occurring isotopes for barium, at least according to the Web Elements website that I just checked out. So basically, we are simply multiplying the mass number of each isotope, which would be these values, times the percentage, but again, I want you to put that into a decimal form. So if you want to just write down those two columns there and just simply replace the percentages with the decimal form. So 0.106, remember, would be 0.00106 in decimal form. 0.101 would be 0.00101. 2.417 would be 0.02417. 6.592 would be 0.06592. 7.854 would be 0.07854. 11.232 would be 0.11232. And 71.698% would be 0.71698. Now, just looking at this, let's make a prediction going in. And again, you really want to do this before you start because there's a lot of places you could go wrong in a multi-step calculation. Give yourself sort of a sanity check before you start and say, all right, 71% of the atoms have this mass. So I'm going to expect my average to come out fairly close to 138, although because all of the other isotopes are lower than 138, 8. I'm going to expect the average to be less than 138, but it should be like 137 point something, but fairly close to 138, like 137.7, 137.8, 137.9 would be a reasonable answer to expect. But basically, for each one of these, I'm multiplying the mass number times its relative abundance turned into a decimal, and then I'm just going to add it to the next one. And I do this as one gigantic string in the calculator. Again, if you want to break it down and do it as a series of discrete steps, you would take the 130 times 0.00106, but then you have to write down that intermediate answer, and it's a lot more writing. It's actually, and a lot more chances for you to go wrong with a copying error. I would recommend just doing it as one long calculation string and just maybe do it 2 or 3 times and make sure you're getting the same answer and make sure your answer makes sense. So I'm going to pause, work out the answer, and you do the same and see what we come up with. Alright, so I did it twice and I got the same answer both times, and I'm feeling pretty good about 137.42162. Although, for significant figure-wise, I'm not sure whether we can really go much beyond 137.4 based on the measurements that went in. And actually, these only had even 3 sig figs up here, so maybe 137. And so it was interesting, my prediction was wrong, and I was thinking about this as I was working it out the second time. There are still some fairly good percentages down here, 6.5% and 7.8%. Of much lighter isotopes, so that's skewed it down closer to 137. Even though 138 was still the most predominant isotope, and I think this is an interesting problem because if you were just looking at the published value on my periodic table, it actually lists 137.33, I think, as the average atomic mass of barium. It's close to the calculated value that I got here. You would think then that rounds down to 133, and so that barium 133 might be the most common isotope, and in fact we can clearly see, barium 137 would be the most common isotope because 137.4 is closer to 137 than it is to 138. But if we would be wrong in that case because there's so many isotopes here, and a good number of them are, in fact all of them, are less massive than the most predominant isotope, which is the barium 138. But you know what? The good news is, from the standpoint of the chemist measuring out some barium, he doesn't really care, or she doesn't really care, what the exact mass of the isotope is, because they're all present in a sample of barium in these proportions. So using 137.4 or 137 point whatever the published value is in the periodic table actually gives very good results because we've got a mixture of all of those isotopes in those proportions. But still, it gives you an interesting problem doing a weighted average. And so the main point I want you to take from this is the weighted average is going to be the mass number multiplied by the relative abundance, which would be the percentage turned into a decimal, and you're just going to sum this up for all isotopes. So when you come into class tomorrow, we're going to have some sample problems for you to work out, which will involve the same kind of math and doing the weighted average. So until then, have a pleasant evening.
Okay, so here's our PVQs for this lesson. We're going to have you calculate the average atomic mass of boron 10 and 11 using the proper equation for this.
Just like we just demonstrated. Just a note, on the very first slide, it said something like 3A.4.
34.8.
This is video 3.5. You watched the right one. We just were unable to correct the misnumbering at the beginning of it.
All right.